Okay, we're team 6. We have Alessandro, Jake, Hayden, and me, Malika, and we're doing an educational video on impulse and momentum.
An object in motion will stay in motion at a constant velocity unless acted on by an external force. Similarly, an object at rest will remain at rest unless acted on by an external force. As you can see, no forces are applied to the chair and the chair remains at rest. So let's get things moving. A force from a push is made to the seated individual in a rolling chair. This causes the chair to move. You might be thinking, what about Newton's third law? This tells us that every action has an equal and opposite reaction. In the case of a simple push, not only is there a force being applied to the chair from the person pushing, but also an equal and opposite force applied to the person pushing from the still chair. Why is this person not moving? Well, this is because of friction. Friction is responsible for keeping the person still, as well as eventually slowing down the chair. This is a whole nother topic, and we will ignore this concept for now.
Now that our chair and seated person are moving, let's introduce momentum. Momentum is defined as the quantity of motion an object has. It can be calculated by multiplying the mass times the velocity, and the formula for momentum is known as P equals m times v. What will happen if this chair collided with another object? In a collision, momentum is conserved. This means that the total momentum before a collision is equal to the total momentum after a collision. In other words, the sum of the mass times the velocity of each object in the system is the same before and after a collision, as you can see in this equation. The two basic collisions we'll be looking at are elastic and inelastic collisions. Elastic collisions include two bodies that collide and then move separately after the impulse occurs. On the other hand, inelastic collisions can be viewed as the two objects sticking together and moving as one body post-impact. In this video, the chair with a backpack starts at rest with no momentum and the seated person is in motion with momentum. After the collision, the momentum of the seated person is shared with the chair holding the backpack and both objects move as one. The seated person has less velocity after the collision because some of the momentum was transferred to the other chair. This is an inelastic collision, however, the chairs do eventually separate due to friction.
Next, we see the same seated person collide with another seated person. Like before, only one of the chairs initially has momentum. However, this time there is an elastic collision. The chairs separate after collision with almost all of the momentum of the moving chair transferred to the seated chair. Again, the force of friction caused both chairs to eventually lose their momentum. As you can see, since there is more mass in the system, the total velocity after collision is less than in the previous demonstration, even though the momentum is the same. You have probably noticed that objects typically don't maintain their momentum forever. So what causes a change in momentum of an object? An impulse. Impulse is defined as a change in momentum and consists of a force applied over a certain amount of time. This relationship is shown by the equation. In our next demo, two people in chairs initially at rest will apply an impulse against each other to increase their individual momentum. As a system, however, their total momentum is still zero because they have velocities in opposing directions that cancel out. Momentum is conserved.
Inertia is an object's tendency to resist a change in motion. Inertia can be thought of as how hard it is to slow an object as it travels, or how hard it is to get an object moving from rest. Momentum must be conserved even in two dimensions. In one dimension, the two objects have a single momentum, either positive or negative. In two dimensions, there are components to the momentum due to velocity being a vector and having a direction associated with it. If the coordinate plane is x and y, then the components of momentum in the x direction must be conserved through the collision. Similarly, the components of the momentum in the y direction must be conserved through the collision. This demonstration is quite simple. You really only need a couple rolling chairs and maybe a few different weighted objects. After that, it's all about colliding them. Thanks for watching.